In topic 2, we're going to look at some periodic table trends. So some other sort of patterns that we find on the periodic table. But in order to understand some of these trends, we're going to have to know what an ion is. So we're going to start in video 3.3 here talking about ions, and then you'll kind of go back and look at the trends. So remember, as a review, from Unit 2, we learned the word isotope, right? Where an isotope is an atom of the same element with different numbers of neutrons. So when we were filling out our tables and we were counting the numbers of things, like maybe we looked up and we saw, we had sodium and its chemical symbol was Na, and then we looked and we saw, let me just make some headings and make a little table here. So you've got the name, and you've got the symbol, and then we had like the Z number, and then we had to fill in the A number, and then we had protons, and we had electrons, and you had neutrons, right? So that kind of looks like one of the tables that you filled out in one of the previous worksheets in Unit 2. So sodium, and we looked and we saw, okay, sodium is number 11 on the periodic table. Maybe sodium in this instance has a mass of 23. Again, that would be of one specific isotope. So it's going to have protons that are equal to the Z number. And then we always kind of assumed that the things were electrically neutral, which meant that all of the protons equaled all of the electrons so that the charge would end up being 0. So we had 11 protons, 11 electrons. And then to get the number of neutrons, it was we used our mass. So protons and neutrons together would equal 23. So the number of neutrons would have to be that. So maybe we had an isotope of sodium that had a mass of 22, and then it only had 11 neutrons, but the protons and electrons stayed the same. So what we're going to move into now is what if this number changes? So an ion is an atom of the same element. So an atom of the same element, but with different numbers of electrons. And the amount of electrons that either get added to or removed from an element is very predictable based on what kind of element it is and its location on the periodic table. So we have metals, and metals are elements that are going to, remember, they're on the left-hand side of the periodic table, and they are going to lose electrons. We'll talk about how many here in a second. All right. We have nonmetals then, right? Remember, those are up and to the right. And nonmetals are always going to gain electrons. Well, the reason why metals and nonmetals are either losing or gaining electrons is to achieve stability. Right? So they want to be like stable elements on the periodic table. So what they're trying to do is trying to achieve a noble gas configuration. So we say achieve a noble gas configuration. Ran out of room there. So they're trying to achieve a noble gas configuration. So remember that noble gases are way off on the right-hand side of the periodic table. So they are actually going to have 8 valence electrons. Let's just look at our periodic table here really quick. So this is column 8, right? And so they have 8 valence electrons, which is what makes them stable. So the metals over here, they're going to tend to lose electrons until they become like this or have a full shell of 8. Or nonmetals up here, they're going to gain electrons until they have a full shell of 8. So they're trying to achieve that number 8. So we actually call this the octet rule. All right, so they're trying to fulfill this octet rule. So we can look at, let's actually just kind of use the examples of sodium and chlorine. So let's start with sodium. So sodium, if we look on our periodic table, oops, my lights went off. There we go. We look on the periodic table. Sodium is right here. Like I said, it's number 11, right? It's in our very first column. And so sodium is going to have 11 electrons. So let me just draw out kind of a noble or like a Bohr's model of it. So sodium has 11 electrons, so it's got 11 positive protons in the nucleus on the inside, and then it's got 11 electrons. 2 go in this first shell, and then in the second shell, we know we can fit 8, right? And then in the last shell, there is that 11th electron. Right? So we have a total charge of negative 11. Okay? So for sodium to achieve a noble gas configuration and have 8 in its outermost shell, what it's going to do is, like we said, metals, they lose electrons. It is going to lose its outer shell, so it's just going to get rid of this shell right here, and it's going to get rid of this electron, right? We'll just draw it kind of going over here. I'll show you where it goes later, right? And so here, this is the ion for sodium that has 1 less electron, so now it only has 10 electrons. So if you have 11 protons and you have 10 electrons, that means you have 1 more proton, and so you're going to be positively charged. We actually call an atom that forms a positively charged ion a cation. And remember, these are all metals. All right, so let's look at then how do nonmetals actually achieve this. So let's use the example of chlorine. So chlorine is number 17 on the periodic table. It's a halogen. It's in column 7, so it's right here. And if I do, it's got 17 pluses in here, right? So 17 protons in the nucleus. And then let's draw the 17 that are outside. So we got 1, 2, and then in the second shell, we've got that 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm up to 10. And now we're going to have 7 more out here. So we've got 1, 2, 3, 4, 5, 6, and then 7. So 1 lone guy. So this is a nonmetal, and what it wants to do is have that outer shell fulfill that octet rule and be like a noble gas. So it's going to gain electrons until its outer shell is full. So basically, where did that negative electron here go? It's going to come over here, and it's going to go into this chlorine. So at first, we had 17 protons and 17 electrons. Well, now I have 17 protons and 18 negative electrons. So you're going to have an extra electron, which means you're going to have a negative charge. We call those an anion, and these are all non-metals. So if I was going to actually write the symbol with the charge for the ion, we would say this is sodium. It has a +1. This is a sodium ion because it's gained it's lost 1 electron. Whereas the chlorine over here, the chlorine has picked up an electron, so it's going to have a -1 charge. So we write it like this. And we call this a sodium ion. And over here for our nonmetal anions, we call it a chloride ion. We change the ending to IDE, and we call it a chloride ion. Now, if you look at the relative size of the atom and then the ion that it forms, actually with cations, what happens is the ion is smaller than the atom. So the ion is smaller than the atom, and it's because it loses a whole shell. It's going to lose an entire shell. Over here, the chloride ion, sorry, you can't see that. Let me move it a little bit. The chloride ion, actually, it's going to gain an electron. This ion becomes larger. So maybe I should write cation is smaller than its atom, and an anion is larger than the atom. And it's because now the nucleus has to pull on more electrons. It's not because it has more shells or anything. It's just the nucleus is pulling on more electrons, which makes its overall pull on each one a little bit weaker. So it just can't really hold on as tight. So it expands just a little bit, right? Now, we'll actually come to learn here in as the unit goes on that when sodium gets rid of an electron, it doesn't just go out into the wind and disappear. It's actually got to give it to something. So when chloride comes near sodium, sodium gives the electron away and chloride takes it. And when you have a positively charged thing here and a negatively charged thing there, opposites attract, they are attracted together, and they actually form an ionic bond, or what's called an ionic compound. Right? Now, let's look at the periodic table one more time, because I want to show you that how we can use the periodic table to actually predict what the charge is going to be on each one of these ions pretty easily. And this is predicted based on its location, the number of valence electrons, and these charges are actually called the oxidation numbers, right? So the charges, I'll just write that up here. Charges are also called oxidation numbers. So remember, they're always wanting to be full, right? So this, in the first column, they all have one valence electron. They all have that in common, right? That's why they have similar properties. And so in order to become full, they're going to dump off their whole shell and they're going to get rid of one electron. So everything in the first column is going to have a charge or an oxidation number of 1. Everything in the second column, they've got 2 valence electrons. They're going to get rid of both of them and they're going to have a charge of +2. We're going to skip over these transition metals around here. They act kind of weird. We go over here, we have a couple of metals in group 3, aluminum being the most important one that we'll actually use most often. It is a metal, it's going to lose electrons, it's going to have a +3 charge. In this row right here where you have 4, again, these are a little hairy on whether or not they're going to be positive or like how many they're actually going to lose. They don't often form ionic compounds that we're going to talk about, and lead and tin can get a little weird. But a lot of times we say these are +4 or -4, but again, I'll talk more in detail about them later. Then when you move into column 5, they have 5 valence electrons. So the nonmetals here, they want to have 8, so they're actually going to gain 3. And by gaining 3, you're going to have a -3 charge. And then in column 6, they want to have 8, so they're going to gain 2. Column 7, they're going to gain 1 to have 8. And then these guys don't do anything. They don't form any charge. Right? So that's an introduction to ions and what kind of atoms form ions and why they form ions. And then we'll go later into forming of ionic bonds and how to predict those.